Okay, so we now moving on into the next speaker. So Professor Schuler. Professor Schuler is a IEEE Fellow, ISKA Fellow, BCS Fellow. He's also a professor and head of the Chair of Embedded Intelligence for Healthcare and Well-being, University of Augsburg, Germany. He's a professor of artificial intelligence and head of GLAM Group on language, audio, and music in Imperial College, London. His presentation will be on the topic of audio intelligence in the wild, from health to the environment. So, Professor Schuler, are you there? Hello. Jessica or Jack from AAIA, could you help me to check whether Professor Schuler is here? Okay, while we're waiting, I think everybody is now muted. No, not everybody. So I'm going to ask people who haven't muted yourself, who are not the speaker. So I'm going to call off names. So if you're listening, could you mute yourself, switch off your mic? So Kevin and Anna, AAIA, which is a common account, I suppose. Another one is called iPhone, and Mike Lee. So if you haven't muted, mute yourself, please mute yourself so you wouldn't interrupt the speaker's flow. Okay. So
Professor Wang, this is Luke Pham from Birmingham. I checked the list of participants and I could not see Professor Schuler on the list.
Okay. All right. Thank you very much. Thank you for your support. In that case, could I invite our next speaker? Unfortunately, the time's probably a little bit ahead of your time. So I would
that is
like
me.
to speak.
That is me. Yeah,
okay.
I just spoke.
Really? Okay. Oh, that's lovely. Thank you so much. So may I take a time to introduce Professor Pham, a Fellow of the Royal Academy of Engineering, Learned Society of Wales, Society of Manufacturing Engineers, Institute of Engineering and Technology, and Institute of Mechanical Engineering. He's all the fellows of these organizations. He's also the Chance Chair of Engineering, Department of Mechanical Engineering, University of Birmingham, UK. His topic will be on intelligent manufacturing and production optimization using the Bayes algorithm. So, Professor Pham, the floor is yours.
Thank you very much, Professor Wang. If I may, I just switch off my camera for now while I'm presenting, just to preserve the bandwidth. So I will try and share my screen. Can you see my screen yet?
Yes, we can.
Oh, thank you very much.
Okay.
So thank you very much for the introduction, Professor Wang. My talk is titled, as Professor Wang mentioned, the focus is on the Bayes algorithm. The applications, there are many applications, and I will mention them briefly as we approach the end of the presentation. So the aim of the talk is to introduce to you the Bayes algorithm, which is something that we developed with our bees. And normally I put all the names of the bees on the front page because it is their work I'm presenting. But because there are so many of them, I just list them here. And we have bees and honorary bees as well. So honorary bees are the people who came and visited us, and the bees are our PhD students and research colleagues. So there are many of them over the years. The Bayes algorithm was developed in 2005, and since then we have had many versions and many applications. I would like just because not everybody knows about the algorithm, I'd like to spend the time that I have today on describing the algorithm to you. It's a very simple algorithm for optimizing all kinds of problems. Then at the end of the presentation, I will say a few words about the applications in the area of manufacturing and production for you. So the bees algorithm, to understand it well, we need to know the bees foraging behavior on which the algorithm is based, or it is inspired by this behavior. Then I explain to you the basic bees algorithm, the very first algorithm that we developed, and then some more advanced features. So the behavior that we copy in the bees algorithm is the foraging behavior. And foraging bees, as you know, they go around, explore the field around their hive and visit different patches of flowers. So these are the scout bees that fly around. You can see them, they fly randomly to different patches, and the distance from the hive of the patches could be up to 10 kilometers. After they have visited some interesting patches, they go back to the hive and they perform what is known as a waggle dance. So you can see here, we have these bees and they have been around and they now go back and do this dance. You notice the figure of 8, which is typical of the dance. It was discovered in the 1930s by von Fritsch, who won a Nobel Prize for the discovery. So the dance, the aim of the dance is to recruit bees who are in the hive to go and exploit the patches that these scouts have found. And you notice that some scouts dance in an excited manner, like this one here, the little one here. And that means it has found a very, very promising patch. And this also has found some interesting patches, but perhaps not as promising as the patch found by this one. The idea is the bee that has found a good, very interesting patch, a rich patch, will recruit more bees to that patch to exploit it more efficiently. So you see in the next slide, that small bee, which danced excitedly, found a very good patch. So it recruited quite a lot of bees to come with it to exploit this patch. Another bee found also a good patch, but perhaps not as good, and it recruited a few bees to the patch. So the idea of the bees algorithm is this recruitment process. When a good solution is found, which is a good patch, then we start exploiting it as much as possible. So this is all there is to this algorithm. And of course, the dancing of the bees is a recruitment process that does not happen in the computer. There's no dancing in the computer. There is randomness, the scouting of the bees, the sending of the bees to scout the field is done in the algorithm. So I show you now the flowchart of the algorithm. It's very simple flowchart. You see that at the beginning, we generate some random scouts. And then we send the scouts to the field. And this is where the scouts have found some patches, and the scouts have now recruited some bees to follow them, to exploit the field. This process is a local exploitation process. And then there is a global exploration process. And this is done by the remaining bees that are not that have not found good patches. So they are now sent around randomly to look for food somewhere else. I will illustrate this with a very simple example. So here is a function, one-dimensional function, and we try to find this peak of the function. We don't know where it is because this is an optimization problem. We don't know where the peak is, but we are looking for it. And we have randomly generated these scouts. So these are scouts. In this case, we have 10 scouts. And you notice that these square scouts have found good solutions, better solutions than the stars here. So these stars have found some solutions, but they are not as good as the top scouts. Then you see also these blue scouts. They are the very top scouts. So we have the top scouts and the very top ones. The very top ones will be able to recruit more bees to follow them, to exploit this area and this area. And these scouts will exploit these areas, but with fewer bees. So you see on the next slide, the neighborhoods are built around these scouts, and they have gone back to the hive, and they have now recruited bees to come with them. So these blue scouts have found more bees, and these white scouts have found fewer bees. At the end of the process, the top bees in each patch are selected for the next generation. And then we have randomly generated more scouts. So the process continues until we reach the top. So this is all there is to this algorithm. Now, of course, there are more strategies to help the algorithm work better. We have neighborhood shrinking. So if we have a patch that does not yield good solutions after a few iterations, we start shrinking it. We start focusing more and more, reducing the neighborhood. That circle that you found, that you saw on the previous slide, it gets smaller and smaller, so that the scouts will recruit bees to a smaller patches and intensify the search around that patch. Now, after a few iterations, if that does not produce a good solution, the scouts will abandon the sites, will go somewhere else. So site abandonment is a process created to avoid the scouts being stuck in local optima. Then the search operations at the in the neighborhood, there are many different search operators that can be used. Mutation of the scout, crossover, interpolation, extrapolation, all kinds of operations can be invented. So this is where researchers can improve the bees algorithm. And we have had several researchers around the world who have worked on the bees algorithm and who have produced new versions of the bees algorithm. Even you can use the Kalman filter as a local search operator. Then another strategy is to have young bees, to protect the young bees that have been generated. If they are newly generated, they may not be as strong as the older bees, and we need to protect them in order for them to compete effectively later on. So this is another strategy for improving the bees algorithm. Now, you can compare the bees algorithm with other algorithms that are very well known, say the ant colony algorithm or the particle swarm optimization algorithm or the genetic algorithm. Several algorithms have been compared against the bees algorithm. We have three main differences. In the case of the bees algorithm, there is no need for an interaction medium. There is no pheromone exchange, nothing like that. And the original version of the bees algorithm, there is a clear distinction between exploration and exploitation. I showed that on the flowchart. You saw exploitation of the neighborhood and exploration of the global space. And then there are other mechanisms that I have mentioned to you to avoid local optima. The bees algorithm has been hybridized with many other algorithms, including ant colony that I mentioned before, particle swarm optimization, genetic algorithm, the Adams algorithm, and so on. Many different algorithms have been hybridized with the bees algorithm. The problem of the original Bayes algorithm is that it has many parameters that the user needs to choose. However, as mentioned here, it's quite easy to choose these parameters. Although there are many of them, they are quite easy to select. And then the strategy, the search strategy of the Bayes algorithm is very effective. It is very efficient, and the algorithm is suitable for searching complex spaces with high and steep valleys and many local optima. As I mentioned, there are many applications of the Bayes algorithm. It has been used for continuous problems like mechanical design, control system tuning, digital filter design, classifier training, including the training of deep neural networks, combinatorial problems, mainly in the area of manufacturing, as you will see on the next slide. So many applications of the Bayes algorithm in production engineering, for instance, the processes, manufacturing processes like electro-discharge machining, hydroforming, metal cutting, turning, milling, and so on, robot control, robot design, then combinatorial problems such as sequencing of printed circuit board assembly machines, classifying of defects on the production line, production planning and scheduling. So many applications, and these are the recent ones. It's too many for me to go into detail for any one of them. If you are interested, there are books published on the Bayes algorithm. Each year we hold a workshop. Next year's workshop is in November, and you are very welcome to attend. It's all free. If you have material to present, you are very welcome to present it. Or if you just want to attend to learn about the Bayes algorithm and its applications, you're very welcome to do so. So in this short presentation, I've explained what the Bayes algorithm is. It's an algorithm based on the foraging behavior of honeybees. It's very simple and has been applied to many problems. So far, we have counted more than 500 applications. We have some new versions of the Bayes algorithm, such as a super fast algorithm, which can be used online in real time, and a very simple version of the Bayes algorithm with only 2 parameters for people to select. So just in case you did not catch the previous slide about our workshop, here it is, and you are very welcome to attend, and hopefully you will become a bee one day. You'll contribute to the development of the Bayes algorithm. Thank you very much, Professor Wang, and the audience. Thank you.
Thank you very much, Professor Pham, for your excellent presentation. We actually have 2 more minutes in the allocated time for you. So I'm wondering whether anybody want to ask a question. Any burning questions people would like to ask about this Bayes algorithm is fascinating, actually. Yeah, so thank you very much, Professor Pham, for your wonderful presentation. So anybody want to ask question? Or maybe you prefer to ask through chat. Yeah.
Sure.
Okay.
Yes. I will put my email address, and colleagues are welcome to contact me about the Bayes algorithm. Thank you.
Brilliant. Yeah. Thank you very much. Thank you.